Hello everyone and welcome back to my channel Gyan Sampada. In our previous classes, while we were discussing about semiconductor devices, we came across the concept of p-n junction, in which we understood how p-n junction is formed and what are the different types of p-n junctions, with the explanation of diffusion method, and our main concentration was on p-n junction at equilibrium. So while studying that, we came across the concepts of the charge density and the space charge region, and also the potential hill which is caused by the charge distribution. And we also understood about the formation of potential barrier or the junction barrier, which was due to the diffusion. So as such, the electric current cannot flow as there is no external electric field which is applied to the system. But still we observe the voltage developed across the junction. So we can say that it is something like a fictitious battery which has the voltage VB, that is barrier potential. And now the question arises that whether this space charge equivalent battery is going to be able to deliver any kind of current when it is connected in a circuit which doesn't have a battery, because there already exists some amount of voltage which is developed across the junction. And in order to answer this question and to understand in more detail, we need to consider the energy level diagram for p-n junction. So when we say energy level diagram, first thing which comes in mind is the valence band and the conduction band. So p-n junction is nothing but a junction which is created by joining p-type and n-type semiconductor. And we know that if we consider p-type semiconductor with top of the valence band having energy EV and the bottom of the conduction band having energy EC, then Fermi level is going to lie just above the valence band, which is due to the acceptor impurities which are added to an intrinsic semiconductor. And if we consider n-type semiconductor, then the Fermi level is going to lie just below the conduction band, that is near to the donor level. So it is clear that the Fermi level in both the semiconductors are at different positions with respect to the band edges, that is with respect to the conduction band and valence band. And we know that Fermi level is something like a potential, and that is the reason it must be at the same level if you consider any system at thermal equilibrium. So when p-n junction is in thermal equilibrium, the Fermi level should be in same level. That is, it should be straight when p-n junction is formed and not down or up with respect to p and n type. So what happens when p-n junction is formed? So after forming a p-n junction, the Fermi level in n-type is at higher position, as you can see here, and the Fermi level of p-type will be at lower position. But at equilibrium, that cannot happen. So something has to take place which brings the Fermi level at same position. And because of this energy difference, electrons will flow from the material which has higher Fermi level or higher potential to a level with a lower potential until they attain a common level. So here we can observe that at thermal equilibrium, after formation of p-n junction, we observe that Fermi level is situated at the same position, whereas separately they are at different positions with respect to the band edges. So what is happening here is that the conduction band of p-type region is shifted upwards by an amount of EVB, where VB is the potential barrier or barrier potential over the conduction band of N region. So this is the amount of shifting which is explained with respect to barrier potential. And according to the energy level diagram of p-n junction, the minority electrons in the conduction band of p region is having higher energy when compared to the electrons present in the conduction band of n region, because along y-axis we are having the increase in energy, and clearly we can observe that electrons present in the conduction band of p region are at higher energy when compared to the electrons present in the conduction band of n region. And here delta E explains the energy difference between the intrinsic Fermi level with respect to the Fermi level of p-n junction. Because we know that if we want to get n-type or p-type semiconductor, we just dope it with some impurities. If impurities are not present, then the Fermi level lies at almost center of the energy gap. So that is denoted here by dotted line, and delta E is the energy difference between the intrinsic level and the Fermi level of the p-n junction. So here we can observe that the band edges in the two samples are going to shift themselves to make this alignment possible. So this is the theory part when p-n junction is formed. And now we will see when the electron is flowing from p to n or n to p, what all factors come into picture. So let's understand about the consequences by a short derivation. Let us consider electron flow from p to n section. So there is a flow of electron, means it is nothing but current, and this current will be proportional to the electron density in the p region as well as the probability factor. So the electron current from p to n can be given as IE is equals to C into exponential of minus E by kBT, which we are calling as equation number 1. So as I told you, this current is going to depend on electron density as well as probability factor. And in this case, when we are considering the flow of electrons from p to n region, the probability factor is going to be equal to 1, because the electrons on p side are having higher energy when compared to the electrons on n side, as we have seen in the previous slide. And the number of electrons in the conduction band of p type is very small, and that is proportional to exponential of minus E by kBT, where E is the energy difference between the lower edge of the conduction band of the p type and the Fermi level. So as we are concentrating on the conduction electrons, we will consider this E as the energy difference between the Fermi level and the conduction band of p type. And now let us consider the electron flow from n to p section, that is from right to left. And here the current is in opposite direction, so vectors are in opposite direction, which will be equal to C into exponential of minus of E minus EC minus EF divided by kBT into exponential of minus EC minus EF by kBT, which we are calling as equation number 2. So here the charge density or the density of electrons is proportional to the exponential of minus of EC minus EF by kBT, or just we can write EF minus EC by kBT. That is the second term. And the probability that the electrons will have sufficient amount of energy to climb up the hill, because electron must have some extra energy to climb and come back to the conduction band of p side. So the sufficient energy to climb up the energy ladder, which is having a height of E minus EC minus EF, is proportional to this first term, based on which we define the electron current from n side to p side. And to understand the relation between the two, let us consider the same equation, that is equation number 2, and here it is something like e raised to x into e raised to y. So that will be nothing but e raised to x plus y. So we can just add those things. So minus e, minus will become plus ec, minus is minus ef, minus c, minus of minus plus ef. So ef and ef will get cancelled out, and also ec with ec. We are remaining with c into exponential of minus e by kBt. And if you look at equation number 1, we can say that the electron current from n to p is equals to the electron current from p to n. And thus we see that there is no net current flow across the junction because of the space charge equivalent battery, that is due to the depletion region. And this shows that the PN junction is in equilibrium state. So here we have considered with respect to the electrons. In the same manner we can consider with respect to the holes also. The same argument is going to be satisfied for holes. So main thing is the conclusion of this derivation. And everything is understood based on the energy level diagram of PN junction. So these are some of the details about the characteristic property of PN junction at equilibrium, and in our next class we will study about the barrier potential at the PN junction at equilibrium. And this is it for today. See you in our next class with more physics related information. Till then, stay tuned, study well, and thank you for watching.